and one clump of cells is found in that piece of nephron. These are known as the granular cells or juxtaglomerular cells, and these are stretch receptors. If you have a stretch receptor in a vessel, what is it really measuring?
Pressure?
Blood pressure. Where does it make sense to measure blood pressure? In the vessel supplying the capillary bed or the vessel draining the capillary bed?
Supplying.
Supplying. That's how you can tell the difference between an afferent and efferent arteriole, because only one of them is going to have a stretch receptor, and that's the afferent one. All right, well, why would it make sense to measure pressure in the afferent arteriole?
You don't want heavy flow going inside. You want to regulate what goes in.
So that is going to be feeling.
These series of cells here measure the stretch, which basically measures the pressure here. And the last thing you want is an overabundance of pressure in some of these vessels.
So is it interacting with that thing on top? Why is it so close? You said it's a unit.
We'll get to that.
Oh.
Yeah.
It's not the.
Okay. Oh, and I'm realizing I should have done something else here, but that's okay. We'll get to that.
So that way it doesn't
Burst these capillaries, yes. But also, it's just a way to measure filtration, because if you see stretch happening here, meaning the pressure in here is high, what does that tell you about the amount of leakage coming out of here?
It's a lot.
It's a lot. If you measure low stretch here, which means pressure is a little bit lower here, then we get less leakage. So it's not just a way of measuring pressure, it's also a way to measure filtration. Because higher pressure means more filtration, lower pressure is going to mean less filtration. The cells in here are called macula densa cells, and they measure salt. Now here's what's important about the fact that we're measuring salt not at the beginning of the nephron, but at the end of the nephron. Is salt going to be waste or nutrient?
Nutrient.
Oh, it's both, isn't it? No?
Well, you want to get rid of excess salt,
Right.
but salt is something that you need, so it's technically a nutrient. It's an electrolyte, but it's needed, right? So, if that's the case, you don't just want to literally put a bunch of sodium into your urine. So, if these cells are measuring salt, what they're kind of measuring is how efficient have you been doing reabsorption? Because salt is something you should reabsorb back into your bloodstream. So, if you measure high quantities of salt here in the filtrate, what does that say about the amount of salt you've reclaimed into your bloodstream?
Not very good.
It's been not very good. So therefore, would you want to dilate or constrict this afferent arteriole? And why?
You would want to
I would think dilate to
constrict.
Why?
Because you want to reserve whatever salts are coming through. You want to slow down the...
You want to slow down filtration. If you dilate this vessel, more filtration, more filtering occurs, and the filtrate flows through the nephron faster. The faster it's moving,
If you said constricted?
you want to constrict it, but the reason you do is because the more you constrict, okay, well then we'll discuss the opposite. If you constrict this, less filtrate comes out. If less filtrate is coming out, how is that filtrate going to move through the nephron? Faster or slower?
Slower.
Slower. What is that going to say about your blood vessel's ability to reclaim the salt and put it back into the blood?
Going to give it more time and
More time to
opportunity.
do so. More time to do so means the salt levels drop, which means that these cells would measure or see a drop in the salt quantity here. So the idea is, if high salt levels are seen in this macula densa cells, it tells this vessel to constrict, because that will slow the filtration, which slows the flow, which means you reclaim salt more efficiently.
So what's the opposite? Because I was thinking if it dilates, it's going to filter more.
Yes, but then that fluid goes through the nephron faster. And then if a bunch of fluid is going through there with both waste and salts, the blood now is trying to grab
You're not giving it a chance.
nutrients out of that filtrate, but it's flowing by so quickly it can't grab it all.
Okay.
And more of it ends up going to the urine. That's the difference. The faster it goes, you're going to miss some. The slower it goes, the more you're going to claim it back. So the whole idea of measuring salt is that it's a way of measuring how much are you reabsorbing back into the bloodstream. If you get all the way through this nephron and there's still a bunch of salt in there, some of that salt's going to wind up in the urine and you've just wasted some of that. And that means that if you're losing salt, you might also be losing some glucose and some amino acids. So by measuring salt volume here, you're measuring how efficiently you've been doing reabsorption. And the way that you regulate the speed of that is by constricting or dilating the afferent arteriole. All right, so that's this group of structures. Let's look here for a second. The cells that wrap around the glomerulus here get a specific name where it translates to foot cell, and that's where we get the name what for these cells? Podocytes. Literally, it translates to foot cell. All right, well, this is one of those times where, in reality, these yellow cells would be lining this whole thing, but they're only showing it on half. Why? Because if we look closely at these blood vessels here, it's like they've got little tiny pock marks. Why does that make sense? What type of capillaries are these?
What type of capillary?
There are 3 types of capillaries: continuous, fenestrated, and sinusoid.
Sinusoid with holes? No?
That would be too
Not that big.
It's fenestrated.
Fenestrated.
Because they would be small.
Small holes, yes. The thing is, so in reality, these cells, podocytes, should cover all of this. But they only show it on half so you can see the structure of the vessels underneath. All right, well, first off, let's look down here. Notice how it's yellow cells with little blue dots inside. What do the blue dots represent? What part of the cell?
Nucleus.
The nucleus. So notice how there's a lot of yellow here, and every once in a while there's a blue dot here, there's a little blue dot over here somewhere. Those are, the yellow is the cytoplasm of the podocytes, and the occasional blue dots that you see are the nuclei of those podocytes. The thing is, why do they get the name podocyte or foot cell? Is because each of these yellow cells has a bunch of little, what look like toes. Notice how the red lines squiggle back and forth, and it's almost like a little yellow toe on top of a yellow toe on top of a yellow toe on top of a yellow toe, and it's like little interweaving finger-like or toe-like projections. So if I ever say name the cell type, these are the podocytes. Name all the little yellow projections. Those are known as foot processes. Now, notice how no foot process touches another foot process. There's always a little red gap in between all those little yellow projections.
A red gap?
The red squiggling line. Why is it red? Is because you're seeing the wall of the capillary underneath the podocyte. Right? If I do this with my fingers, if I do this with my fingers, you can still see black table underneath. If the little yellow projections of the cells don't quite touch each other, you're seeing the red wall underneath.
Oh, see, that's what I was saying.
Right.
If it was underneath.
Yeah. So underneath these yellow podocytes are the fenestrated capillary. So therefore, what you're seeing as this red squiggling line is not part of the podocytes, it's the gap between the podocytes where you're seeing the red vessel wall underneath.
So does the podocyte cover the vessel like kind of like a sleeve?
But not completely. It leaves spaces, and those spaces are where you're seeing the red line. What's the name of the red line then? A filtration slit. Because how does plasma get out of these vessels and into the Bowman's capsule? Through the gap that is that red squiggling line. So it's called the filtration slit because it's where filtration happens. It comes out of this vessel and into the Bowman's capsule through that red filtration slit. All right, well that's pretty much this whole model right here.
And so that would be the efferent? Or afferent?
Neither. How did blood come into this blood vessel mass here, the glomerulus? In this one, the afferent. The blood comes through here, leaks a lot of its plasma to become filtrate, but what does not leak out then leaves the glomerulus in this, an efferent arteriole.
So once it's inside, it's just all